Hello everyone, welcome to this lecture. Just to begin with, just to recap, in the last lecture we discussed about the notion of partial ordering and we discussed about topological sort. The plan for this lecture is as follows. In this lecture we will discuss about functions, we will see the various types of functions and we will also see composition of functions. So what is a function? So imagine you are given two sets, a set A and a set B. And when I say I have a function, say little f from the set A to the set B, then it is a special type of relation from the set A to the set B. So since the function is from the set A to the set B, we denote it by this notation. Okay. And pictorially you can imagine that we have the sets A and set B. So they may be the same set or they might be different set, it doesn't matter. And what is the speciality about this relation? So I'm saying that the function is a special type of relation from the set A to the set B. So of course f is a subset of the Cartesian product of A and B. Okay, because that's the definition of a relation from A to B. Now this is a special type of relation. The speciality here is that each element of the set A is assigned exactly one element of the set B. Okay, so that means in terms of ordered pairs, if I consider this function f, then each element small a belonging to the set A will appear exactly in one of the ordered pairs in the relation corresponding to this function f, and this holds for every element small a from the set A. Okay, so none of the elements small a will be missing. Each such element small a will appear as part of an ordered pair in the function f. Okay, so we use this notation f of a equal to b to denote that b is the unique element which is assigned to the element a as per this function f, and the element b is called as the image of element a, right, and a will be called as the pre-image of the element b. Okay, so again, to just state the speciality of this relation, each element from the set capital A will appear as part of an ordered pair, as an ordered pair in the function f, and it won't happen that you have element A getting mapped to say element B1 in the function, as well as element A getting mapped to the element B2 which is different from B1 also in the function f. That is possible in a relation. In a relation, the same element small a from the set capital A can be mapped to multiple elements. It can be related to multiple elements from the set P, but the speciality of the function is that there will be only one element from the set capital B which will be related to the element A, and no element from the set capital A will be missing as part of this function f. That means every element will have a corresponding related element from the set P as part of that function. Okay. We also use the term domain and the codomain in the context of a function. So the set A will be called as the domain of the function, while B is called as the codomain of the function. Okay. So notice that all these definitions are with respect to a function from the set A to the set B. The direction of the function matters a lot. As if I say my function is from the set B to the set A, then it should be interpreted as a special type of relation from the set B to the set A, where the ordered pairs will have the first component from the set B and the second components of those ordered pair will be from the set A. Okay, and then the domain will be the set B and the codomain will be the set A, and so on. So now we will be interested to study some important class of functions. So the first important class of functions is the one-to-one or injective functions. So imagine you are given a function f from the set A to the set B. It will be called as an injective function provided distinct elements from the set A have distinct images. Okay, so pictorially you can see here that each of the elements, the small circles from the set A, is assigned a distinct element from the set B as an image. So to put it formally, we want that the universal quantification for all a comma b, f of a is equal to f of b implies a of e implies a is equal to b should hold for an injective function. So what exactly this universal quantification means? It says that if you have two elements a and b whose images are same, then that's possible only if the elements themselves were the same or the pre-images were the same. Okay, or equivalently the contrapositive of the same thing is if you have two different elements a and b, they will have different images. So both these definitions are equivalent. Okay, if you prove any of these two conditions to be true for the function f, and remember both of them are universal quantifications, if any of these two universal quantifications hold for your function f, then we will call the function f to be an injective function. Even if there is one pair of elements a and b for which these universal quantifications are not true, then the function will not be called as an injective function. So you can see why it is called one-to-one function, right? The mapping is unique for every element. Okay, so if I consider the function f of x defined to be f of equal to x square over the set of positive integers, so this set is the set of positive integers. Okay, then what do you think? Is this function a one-to-one function? Well, it is not an injective or one-to-one function over the set of entire integers. Okay, if I consider the set of all integers, definitely this is not a one-to-one function because I have both plus of x getting mapped to x square as well as minus x also getting mapped to x square if my domain is the set of all integers, if my x can take positive values as well as negative values. But if I restrict my function only over the set of positive integers, that means my x can only be positive integers, then clearly this is an injective function. Okay, so you can see the importance of domain. If you change the domain, the interpretation or the meaning or the property of the function changes immediately. The next important category of function are the onto or surjective functions. So again, imagine you are given a function f from the set A to B. It will be called as a surjective function provided the following universal quantification hold. You take any element b from the codomain. Okay, it should have at least one pre-image. That's a condition. Okay, so you can see here in the universal quantification, the domain of a small b is the codomain of the function, and the domain of a small a is the domain of the function. So pictorially, you take any element from the set capital B, there should be at least one pre-image for that element. It might have multiple pre-images as well. So for instance, if you take this particular element, it is the pre-image of two possible elements. It is the pre-image of this element as well as it is the pre-image of this element. Well, that's fine, right? The definition simply says it should not be the case that you have some element in the codomain set, right, which do not have any pre-image. That will be a counter example for this universal quantification. So even if you have any such counter example, the function will not be called as a surjective function. Whereas if this universal quantification is true for all b comma a, where the domain of a small b is the capital B set and the domain of a small a is the capital A set, the function will be called as a surjective function. Okay, so here are two functions. The first function is over the set of integers defined as f of x to be x plus 1. Now what can you say whether it is a surjective function or not? Well, it's a surjective function. So what you can prove is you take any integer y belonging to the set of integers, its pre-image will be y minus 1. That means the element y minus 1 would have been mapped to the element y. And this is true for any y from the codomain set. So that's why the first function is a surjective function or onto function. But the second function is not onto because x square will be only a positive value. So it's only the positive integers from the set of integers which will have a pre-image. The negative integers will have no pre-image. You can't have the square of any number being a negative number, right? So now the question is, how do we prove whether a given arbitrary function is an onto function or not? So we have to check whether this universal quantification is true for that given function. But if the domain and the codomain of the function f is an infinite set, we can't check whether this universal quantification is true for every b and with respect to that b for some a. So what we will do is, instead we will follow the principle of universal generalization. Since we have to prove that the condition is true for all the elements small b from the codomain set, we will instead pick an arbitrary element small b from the codomain set, and for that arbitrarily chosen element small b, we will prove the existence of at least one pre-image element small a from the domain such that f of a is equal to b, right? And since we are going to we will show this for an arbitrary b from the codomain set, that will show that the condition holds for any element small b from the codomain set. That's how we prove whether a given function is an onto function or not. Whereas if you want to prove that a given function is not a surjective function, then we have to find a counter example, namely a counter example for which the universal quantification does not hold. Namely, we have to find out a element from the codomain set, say small b, which do not have any pre-image. Now, the third category of important functions is the 1-1 onto function. They are also called as bijective function. Sometimes we also use the term 1-to-1 correspondence. There are many terms for the same concept. So again, you are given a function f from the set A to the set B. It will be called as a bijective function or bijection, provided f is an injective function. That means this condition should hold. That means different element or distinct elements should have different images, and the function has to be a surjective function. So if I take the function f of x being x, this is also called as the identity function. Why it is called identity function? Because every element is just mapped to itself, and it doesn't matter what is the domain and codomain of this function. This will be always a bijective function. Clearly it is an injective function, because if you have x1 not equal to x2, then f of x1 will be x1 and f of x2 will be x2, and since x1 and x2 are different, hence f of x1 and f of x2 are different. That shows that the function is injective. Whereas if you take any given random or arbitrarily chosen element y from the codomain set, the corresponding pre-image for that y is the element y itself. It shows that the function is a surjective function. Okay. Now we will define what we call as the inverse of a function. So imagine you are given a function from the set A to B. Okay, so since f is a special type of relation, right? Remember, it's a special type of relation. We can find the inverse of that relation as well. So basically we are trying to find out the inverse relation, which I denote as f inverse, but it will be a function. It will be defined as a function. That means it should satisfy the requirements of a function. That means f inverse will be a subset of B cross A, and it will be a function. That means each element is small b from the set capital B will appear as part of as part of an ordered pair in this collection of ordered pairs F inverse. Okay, and what will be the mapping of any element is small b as part of this inverse function? The mapping will be, or the image of that element is small b will be an element is small a, provided small b was the image for that element small a as per the function f. Okay, so it is easy to see that a function f will be invertible if and only if the function is a bijection. If the function f is not a bijection, then we cannot define the inverse of that function. So let's prove this formally. We can show that if your function f is not an injective function, then clearly f is not invertible. So since the function f is not invertible, that means you have two elements in the domain, say a1 and a2, which are different but getting mapped to the same element small b. As far as the function definition of function is concerned, this is allowed, right? I am not saying my function f is an injective function. Here I am assuming my f is not an injective function. So if it's not an injective function, that means this is possible. But if this is the case, what can you say about the inverse of b? Will you say f inverse of b is a1, or will you say f inverse of b is a2? You are ambiguous here. It's ambiguous here. We can't find out the image of the element b as per the f inverse function. So f inverse will not be defined. I stress that if this would have been a relation, then it's absolutely fine. If would have been a relation, then in f inverse you could have b comma a1 and you could have b comma a2 as well, because in relation there is no restriction, but f inverse has to be a function, and you can't have two images for the same element if it's a function. So clearly this shows that if your function f is not an injective function, that it is not invertible. We can also prove here that if the function f is not a surjective function, then also it is not invertible. So if it is not a surjective function, that means you have some element, at least one element is small b from the codomain set, right, which do not have any pre-image. If that's the case, then what can you say about the image of the element b as per the f inverse function? It's not defined here, but that's a violation of the definition of inverse of a function. So that shows that a function is invertible if and only if f is a bijection. Okay. So the last thing that we want to now define is the composition of functions. So remember, functions are special relations. So since we can compose relations, we can compose functions as well, provided certain conditions are satisfied. So imagine you are given two functions, a function g and a function f, with appropriate domain and codomain. Then the composition of the f function and the g function is denoted by this notation, and this is defined to be a function. Okay, so let me make it more clear here. So you imagine that g is a function from set A to set B, where A and B might be same, they might be different, and f is a function from B to C. Then the composition of the f function and the g function will be a function from the set A to C. And what exactly will be that function? So we will apply the function g first and obtain the images for possible elements A from the set capital A, and then we will apply the function f on those resultant elements, and that will be the mapping of the element A as per the composition of f and g function, right? So this composition of function has to be a function, and it is easy to see that since it has to be a function, then the composition of f and g is defined only if the range set of g is a subset of the domain set of f. So what exactly the range of the g means? So since g is a mapping from, I am assuming here that g is a mapping from A to B, then A is called as the domain, B is called as the codomain. Okay, then what is this range set? It is the set of all images of various elements from the A set. That means this range is a subset. It may be the entire set B, or it might be a proper subset of the set B. So if your function g is from the A set to B set, what I am saying is I am just focusing on all the elements which is a subset of this set B which have pre-images. That means they are the images of some element from the set A, because your function g need not be a subjective function. There might be some elements in the set B who do not have any pre-images. So I ignore those elements when I am considering the range set. Those elements will be considered, this as star elements will be considered as part of the codomain set, right? But they won't be considered as part of the range set. When I say the range set, I am just focusing on the image set, the images that the function g assigned to various elements in it. So coming back to the composition of function, it's easy to see that the composition of the f function and g function is possible only if you take the range set of the g function, then it should be a subset of the domain of the f function. Okay, if your f function is from the set B to set C, then if I focus on this circle thing, each of them should have an image as per the f function. That means that circled thing should be a part of the domain set of the f function. If this condition is not satisfied, then clearly the composition of the f function and g function is not defined. And again, the composition of functions need not be commutative, in the sense the composition of the f and g function need not be equal to the composition of g and f function. First of all, the composition of g and f function need not be defined at all if the composition of f and g is defined, because my a, b, c and sets could be arbitrary. So only under special conditions the compositions f of g may be equal to the composition g of f. Okay. So that brings me to the end of this lecture. These are the references for today's lecture. Just to recap, in this lecture we introduced the concept of sets. We discussed about various special types of sets, and we also discussed about the compositions of relations. Thank you.